Welcome to this explainer. Today, we're going to decode the invisible math that helps machines know exactly where they are in the universe. We're diving deep into the fascinating world of Kalman filter variants. Whether you're tracking a commercial flight, forecasting a massive hurricane, or literally landing a rover on Mars, there's a specific algorithmic brain working behind the scenes to make it all happen. So let's explore how these different filters take incredibly messy, noisy data and turn it into precise truth. Okay, let's take a quick look at our roadmap. We'll start with the Standard Kalman Filter, then move into bending the rules with nonlinearity, tackle extreme complexity and chaos, figure out choosing the right tool, and finally, wrap up with navigating the cosmos. Let's jump right in. Section 1. The Standard Kalman Filter. To really understand how everyday things like GPS positioning and aircraft navigation are even possible, we absolutely have to start with this foundational tool. Think of the filter as the mathematical brain of a navigation system. In engineering, let's face it, you rarely have perfect information. Sensors have noise, and mathematical models, well, they just aren't flawless. So the Standard Kalman filter takes what we think we know from our systems model, combines it with those noisy sensor measurements, and mathematically calculates the most accurate possible estimate of reality. It essentially finds the truth amidst a sea of noisy data. The really cool part is that it operates in a constant loop with a simple two-part heartbeat. Step 1 is the prediction phase, where it estimates what the next state should be based on its model. Step 2 is the update phase, where it takes the brand new sensor measurement and corrects that prediction. It's an incredibly computationally efficient loop, and it is statistically optimal. But there is a catch. It only works perfectly for linear systems with what we call Gaussian noise. Basically, that just means the errors have to fall into a nice, neat, normal bell curve. Section 2. Bending the rules. Non-linearity.
But as we all know, the real world is messy. It's nonlinear. Things just don't move in perfect straight lines with perfectly predictable math, right? This means our standard filter hits a massive wall and needs some serious problem-solving upgrades. So we've got two primary workarounds here. First up is the Extended Kalman Filter, or EKF. It handles mildly nonlinear systems by essentially forcing them to act linear. It uses first-order Taylor series expansions and some pretty complex math called Jacobian matrices to approximate a linear model. But forcing it introduces errors, so we turn to the Unscented Kalman Filter. Now, the UKF, which I know sounds a bit like a brand of deodorant, actually solves the EKF's linearization errors beautifully. Instead of forcing the math to be linear, it uses the Unscented transform. It grabs carefully chosen data markers called sigma points, pushes them through the nonlinear system, and reconstructs the estimate. This captures those nonlinear effects much more accurately, all without needing those tricky Jacobians.
Let's look at how this plays out in a real-world scenario, like spacecraft attitude estimation. Determining exactly how a spacecraft is oriented in space involves highly nonlinear rotational dynamics. But despite those linearization errors we just talked about, the EKF serves as an absolute workhorse here. It takes data from star trackers, sun sensors, and gyroscopes, and it crunches the numbers fast enough to keep that spacecraft pointed exactly where it needs to be. It's relatively fast and incredibly widely used, even though its heavy reliance on Jacobian matrices can cause it to diverge if the system gets a little too highly nonlinear. Now, what if you're dealing with inertial navigation systems? Think the GPS in your car or the complex navigation in a commercial aircraft. Well, the Error-State Kalman Filter, or ESKF, is a brilliant workaround for this. Instead of trying to estimate the entire massive state of a fast-moving vehicle all at once, it focuses purely on estimating small errors or corrections. The MAME nominal state is propagated separately, and the ESKF simply cleans up the minor deviations, like the drift you get in an inertial measurement unit, or IMU. This specific separation makes it incredibly stable for commercial navigation. And then for the highly nonlinear challenges, like, say, tracking a satellite zipping at incredible speeds through shifting gravitational fields, the Cubature Kalman Filter, or CKF, steps up to the plate. This filter uses a really unique mathematical approach called cubature integration to approximate complex integrals. It delivers a much higher estimation accuracy than the EKF, but here's the best part. It doesn't require a massive leap in computing power. Its computational cost is actually similar to the UKF, so it's just a fantastic option for keeping tabs on fast-moving, complex targets. Section 3. Extreme complexity and chaos.
Okay, so we've handled mild and strong nonlinearity, but how on earth do we track environments that are just massive in scale or completely unpredictable? Think about the Earth's atmosphere for a second. How do we predict chaotic, global weather patterns or ocean currents? The standard filters would literally instantly crash under that sheer volume of data. That is exactly where the Ensemble Kalman Filter, or NKF, comes in. Instead of propagating one single estimate, it propagates an entire ensemble of many possible system states simultaneously. By analyzing the statistics of this massive ensemble, it approximates the true probability distribution. It's pretty much the ultimate algorithmic tool for massive, high-dimensional systems like global climate prediction. But what if you're landing a rover on Mars? The terrain is totally unknown, the descent is incredibly chaotic, and the sensor noise, yeah, it's definitely not nicely distributed in a neat Gaussian bell curve. When things get extremely nonlinear and non-Gaussian, we just toss out the normal assumptions entirely and use the particle filter. It literally generates thousands of random samples, called particles, representing every possible state that the rover could theoretically be in. As the actual sensor data comes in, it discards the unlikely particles through resampling and keeps the ones that actually make sense. It's a highly flexible algorithm and absolutely essential for autonomous robots, though as you can imagine, it demands a massive amount of computing power to run thousands of simultaneous possibilities. Section 4. Choosing the right tool. With 7 distinct algorithms on the table now, evaluating the trade-offs is absolutely crucial. This matrix is basically your ultimate cheat sheet. Just look at how computational cost scales up as we increase complexity. If your system is perfectly linear, the standard KF is low cost and highly effective. Got mild nonlinearity? The EKF works great, but notice it is one of the few that requires those complex Jacobian matrices. As we jump into strong and extreme nonlinearity with the UKF, CKF, and ultimately the particle filter, we finally ditch the Jacobians, but a computational cost skyrockets all the way to very high. So, to clearly distill our takeaways here, you always want to match the scale of your system's chaos directly to the right filter. If you're designing an inertial navigation system using IMUs, you go straight to the ESKF. If you're modeling the Earth's complex weather systems, grab the NKF. And if you have a multimodal problem that completely defies normal Gaussian rules, well, there's no way around it. You have to bring out the heavy computing power of the particle filter. Section 5. Navigating the cosmos. To truly appreciate why all of this matters, let's look at how the space engineering industry relies on these exact tools to explore the universe. For determining a satellite's orbit, engineers will rely on the EKF, UKF, or CKF. But when multiple satellites need to fly in a precise formation together, where gravitational forces and atmospheric drag create highly nonlinear dynamics, they strictly use the UKF or CKF. And for the most dangerous task of all, planetary landing and autonomous navigation, they put their trust in the Unscented Kalman Filter and the particle filter. Honestly, without this precise toolbox of filters, everything from landing safely on another planet to coordinating delicate satellite formations would literally be mathematically impossible. From the standard algorithm updating a basic flight path, all the way up to massive particle filters guiding Mars rovers to safety, the math behind estimation is what allows humanity to navigate the unknown. I really hope this explainer showcased the brilliant evolution of these algorithms for you and leaves you wondering, as our autonomous machines venture deeper into unknown environments, what incredible mathematical innovations will power the very next generation of space exploration?